Okay, so today we'll talk about the viscosity solution of past dependent PDE. So today when I got up, I figured out I have a talk in Collège de France. So there's a decision to make whether I take the RER public transport or I drive my car. So you see, if I take the RER transport, we will meet all those daily trouble, accident from time to time, and the passengers will become more and more anxious and worried about whether they can reach the destination on time. And maybe finally you can still reach Collège de France on time because you leave home 2 hours in advance. Okay, but then think about taking your own car. Running on the highway after the rush hour in the morning, you feel incredibly happy just by thinking about those people who take the choice of taking the RER train. But when you're reaching Paris, you find that there's no parking slot in the nearby 5 kilometers around the Collège de France, and you have to pay a very expensive parking bill for your staying there. So you see that from this story, we see the happiness of my morning achievement depends on the path I choose. It's path dependent. And of course, mathematically, it's static optimization. I make the choice at the initial time when I'm still in le guichet. So probably it's not an interesting story to tell in this PDE seminar. What we will consider today is the dynamic programming. So the real motivation for our path-dependent PDE. So let's start from the easiest story, the conditional linear expectation. So V here is the value function of the conditional linear expectation of a utility function H functioning on the Brownian motion W. And we know that this value function V is classically connected to the heat equation. In fact, we can prove that V is indeed a classical solution to this heat equation, and the proof is simply the Ito calculus. And this kind of PDE characterization can simply go beyond the linear case. Let's consider this control problem with the control diffusion X. In the diffusion, we see that there's a drift coefficient B and the diffusion coefficient sigma, and in those coefficients, there's this kappa as a control variable. And the corresponding optimal stochastic control problem is stated as follows. The function V is the value function. The value function is to maximize the conditional expectation of the utility function F and H. So it is connected to the HJB equation, which is fully nonlinear. And under some milder condition, we can prove that the value function V is indeed a viscosity solution to the HJB equation. And we make a little modification to the control problem. Here, still consider a diffusion controlled by the control variable kappa, but in the coefficient B and the sigma, we make the dependence on the state a little bit delayed, which means instead of taking the model with B and sigma depending on the value of xs at the moment s, we consider the dependence on the xs minus delta. So the information has delta time delay. And in this case, we still consider the value, we still consider the same optimization problem and note the value function as V. So it's no longer possible to find a corresponding PDE of a finite dimensional state space. That's why we want to study the so-called path-dependent PDE. So here we will organize our first meeting with the path-dependent PDE. Still, we start from the simplest case, the linear conditional expectation, but of a utility function psi, which is path-dependent. So psi depends on the whole path of the Brownian motion from 0 to t. So t wedge means it's a stopped path. So we want to state the corresponding path-dependent heat equation. And until now, we don't know how to write it. So here is the first observation. The value function V is non-anticipative in the sense that the value of the V depends on the path, but only depends on the path until time t. okay, because the conditional expectation is adapted to the nature of each equation. So now I will introduce the new notion of a derivative introduced by Bruno Dubihe in 2009. So first, let's consider the horizontal derivative, noted as dt of v. So we make a perturbation of this path-dependent function v in such a way. So here in the little picture on the right-hand side, the black path is the path omega until time t, the original path. And then we make a little perturbation by extending the path with a flat tail after time t till time t plus h. And by doing such a perturbation, we do the we consider this limit and define it as a horizontal derivative. And then there's, of course, another derivative considered the omega, which we call it the vertical derivative. So vertical derivative is more easy to define or more natural to define. So here the perturbation is on the path omega at the moment time t. Okay, so at the time t, you make a perturbation of the value of omega t and define the limit as the vertical derivative. So here I note in red the horizontal derivative because there are some delicate issue about this definition. So first, maybe you have already observed in this definition, in the first line of the definition, the limit is only taken from the right-hand side. It's not the limit from both hand side. So more precisely, it is in fact a right-hand side derivative instead of a real derivative. And in fact, there are more stories about it, which we will mention later in the talk. So why we define those derivatives in the Dubihe sense? That's because it leads to the functional ethos calculus. So by using the horizontal and the vertical derivative, we can have formally the same ethos decomposition as the classic ethos calculus. So here we plug any continuous local martingale x into the path-dependent function v, and then the process vtx will have such a ethos decomposition. And now we come back to our linear expectation model. We know that the vtw is a martingale because it's a conditional expectation. So the drift part of this semi-martingale decomposition should be 0. The blue part should be 0. And we know that the quadratic variation of w is just t. Consequently, we can now write down the path-dependent heat equation using the derivative notation proposed by Bruno Dubihe. So formally, it's exactly the same as the classic heat equation. You just replace the t derivative by horizontal derivative, replace the x gradient by the vertical gradient. Okay. So till now we have solved the problem of the linear equation with classical smooth solutions. But of course, we want to go beyond this case. We are interested in those nonlinear equations because we consider those control problems or differential games. And also, in fact, there are very few value functions which are smooth in the Dubihe sense, even for the linear case. It's different from the PDE. So in the path-dependent PDE, even for the heat equation, you can easily construct those examples in which the value functions are not smooth, are not continuous, in fact, okay. Are not smooth. The derivative are not smooth. Okay. So that's why we are motivated to introduce the viscosity solution to the path-dependent PDE. So just a reminder for, maybe it's redundant for this audience, but still want to remind that the viscosity solution is motivated by the maximum principle, and it's defined through sub and super equation. For this talk, that's enough. Okay, and the rest we will remind later. So through this talk, we will be interested in such a nonlinear path-dependent PDE. So it's just a parabolic PDE with a generator capital G with terminal conditions. So in this talk, we will assume that the G is continuous with respect to the variable T omega, and it is ellipses with respect to the the rest of the arguments. And of course, G must be elliptic with respect to the second order gradient. So just to be clear, the ellipsis condition is just to simplify the presentation in this talk. So in fact, in the recent work, we can already go beyond the case of ellipsis. Okay, so let's continue. So before defining the viscosity solution to the path-dependent PDE, we want to go one step back. We need to return to the future and review the definition of viscosity solution of the PDE. So we start from PDE. So again, we take the heat equation, okay, the simplest parabolic equation. And to define the viscosity solution, which is a weak solution, so of course we must first define the test functions. And as I say, the viscosity solutions are defined through a sub and super equation separately. So let's take a sub equation as an example. So now we take the one class of test function noted as A lower bar. So these are those continuous function, this smooth function tangent to u from above at the point of Tx. Or in other words, u minus the test function phi reach its local maximum at the point Tx. And by considering those test functions, phi, if we assume that u is a smooth function, of course it's not, but we assumed in mind, assuming that u is smooth, then since u minus phi reaches its local maximum, then by first and second order condition of this optimality, we know that dt phi should be equal to dtu, and the Laplacian of phi should be bigger than Laplacian of u. So we deduce that the phi function will certainly satisfy the sub-equation. So this is an observation through this simple analysis. So now we assume that we are probabilists which already forget those basic knowledge of basic analysis and how we can recover this orange line by using our probability argument. So this is the line in between. So now, again, we introduce a Brownian motion, W. And since U is a solution of the heat equation, it must be the conditional expectation of some utility function. So this process is naturally a martingale. And then we use the property of test function phi for the first inequality. You see that since u minus phi reaches maximum at T omega, so we have the first inequality like this under expectation, okay? And then since u is indeed a martingale, okay, it's a martingale, so this equality comes from the martingale property. So ut plus tau minus ut under expectation should be 0. So what's left is the expectation of minus phi t plus tau. And then since phi is a smooth function, we can apply the classical Ito formula to obtain this sub equation for phi again. Okay, this is we just replace the classical analysis by a probabilistic argument. But then when we review this probabilist argument, we find something more. In fact, we didn't use the whole information of the test function phi. What we use is, in fact, this in red. So we only use the fact that phi is tangent to u in average from above. So here we can modify the class of test function phi. If we only take we take those phi which so that u minus phi attain the maximum in the sense of mean value. So indeed, the new family of test function a round or lower bar will be bigger than the original one because they are more so those phi who attain the local maximum pointwisely, of course, still reach the maximum in mean value, but there are more candidates for this test as these kind of test functions. So we modify the definition of the test function. As a result, we will modify the definition of the viscosity solution. So here we first record the definition of the viscosity solution. If so, U is called as a sub-solution if for all those test function in the set A lower bar UTX should satisfy the sub-equation at the point Tx, and the viscosity solution is just both the sub and super solution. And now, since we introduced a new class of test function A round the lower bar, now we can replace the old definition by this new one. But remember that in our probabilistic argument, we use the Brownian motion. So in other words, this definition is depending on the Venus measure. So that's why we call it the P0 viscosity solution. So the P0 viscosity solution is defined in a similar way, in exactly the same fashion. So instead of considering those test function in A lower bar, we consider the test function in A round lower bar. And now we want to verify whether it's a good definition. So a good definition, of course, you need the existence and the uniqueness. And in fact, the existence is already verified by our probabilistic argument in the previous page. And now we only consider about the uniqueness. So, and we want that the unique solution selected by this definition should satisfy the maximum principle, of course, because it's the motivation of the viscosity solution. And for both statements, there's a common sufficient condition, which is the comparison principle. Given a sub-solution U and the super solution V, if U is dominated by V at the terminal times, then we say that comparison principle implies U is dominated by V everywhere. Okay, so this is comparison principle, and how we prove it. In fact, it's very easy using the P0 viscosity solution definition. So first, we need a lemma. And it's very easy to prove, just several lines using the optimal stopping argument. We can prove that under some integrability condition instead of more regularity condition, we can prove that the following fact are equivalent. So in fact, U is a P0 viscosity super solution is equivalent to the fact that UT, the process, is a super martingale. It's a P0 super martingale. And the same story for the sub-solution and the sub-martingale. And using this lemma, we can prove the comparison in 5 lines. So given U and V sub and super solutions, and the U is dominated by V at the terminal time, since we have already this lemma, the process UT is the sub-martingale, and the process VT is the super-martingale. Then first we use the sub-martingale property of U to get the first inequality. UT is more than the conditional expectation of U capital T, and then by the dominance at the terminal time, we have a second inequality. So U is more than V at capital T. And then again, we use the super martingale property of the process V to get the final inequality. And then if we read it through, we find the U is dominated by V everywhere. So this is exactly the result of a comparison principle. So very simple to prove here. So we have solved the problem for heat equation, but for PDE, okay. So it's not the story I want to talk today here. So there are extensions to make. There are two extensions to make. First, we want to extend our notion to the path-dependent case. And then, of course, we are interested in the nonlinear case too. So first, the extension from non-path-dependent to path-dependent. So we introduced the canonic space. First, the path space omega, which contains all those continuous path space starting from the origin. And then we denote theta as the product space of time and the path. Okay. And then, of course, this path-dependent heat equation is based on this space. In fact, in order to define the viscous solution to this path-dependent heat equation, we only need to replace the smooth function in the test function family by the new smooth function in the Dubé sense. And in fact, we can do a little bit, we can do it in an even simpler way. Recall that in the classical viscosity solution literature, we have the notion of jet. So in fact, we can do the same thing for the path-dependent PDE. Here, the jets are paraboloids in the path space. So with the coefficient alpha, beta, gamma, so phi, alpha, beta, gamma are paraboloids defined as follows: alpha t plus blah, blah, blah. And we see that, very interestingly, the paraboloid is not path-dependent. It is, it is defined in the path space, but it's not path-dependent. It only depends on the value of the path at time t instead of the whole path. Okay. And we can calculate the Dubé derivative for these paraboloids. The horizontal derivative is alpha. The first order vertical gradient is beta, and second order is gamma. Okay. And in fact, as in the classical literature of viscous solution to PDE, we don't need to consider all those smooth functions as test function. It's only necessary to consider those paraboloids. So here is the same story. We only need to consider those test functions as paraboloids. So the definition of viscosity solution would be equivalent. So here, J lower bar and J over bar are the jets for the sub and the super solution, respectively. And since paraboloids are entirely determined by the coefficients of beta, gamma, we don't need to record the whole function. We only need to record the coefficients. That's why we call it jets. Okay, jets are of finite dimension. So these are finite dimension jets, very important. Okay, so now we can, of course, define the viscosity solution using the jets. And it's already for the path-dependent PDE. Okay, the path-dependent heat equation. So we replace the derivative, the Dubé derivative of the test function directly by alpha, beta, gamma. In fact, in the heat equation, there's no beta, so it's only about alpha and gamma. So this is the definition of viscosity solution to path-dependent heat equation. And it is a good definition. Why? Because we can still prove the comparison principle using exactly the same argument as before. Okay, we still have that lemma about the equivalence between the super martingale and the super solution, P0 super solution, also for the sub solution. And then we have the same argument to prove the comparison principle. All right. So why we prefer this new definition of jet? So there's some philosophical remark here. So by taking into account those test functions which are only tangent to the potential solution in the mean value, we are indeed considering more test functions. So A round bar is bigger than A bar. Okay, we are taking care of more test function, and consequently, there will be fewer viscosity subsolution or super solution. And well, intuitively, it will make the comparison easier to make, okay, because you are comparing fewer pair of functions. And technically, it will become possible because because of this observation. So in the PDE, we consider PDE, for example, on the real space. The real space is finite dimension, of course, is locally compact. And the path space is not. The path space, if we consider using the L infinity norm or LP norm, it's not locally compact. And for locally compact space, you can always find a maximum argument in a compact, okay, in a compact neighborhood. But this kind of argument can no longer work in the path-dependent context, but we have a way to replace it. We can indeed consider the optimal stopping problem and find the optimal stopping time t star to solve the optimal stopping. And this argument can very well replace the argument here in the real space and make the comparison works, okay, and it works easily. So now we do the second extension from linear equation to nonlinear equation. So to do that, we will replace the P-naught measure. So before we are only talking about heat equation, it's always the definition depends on the Venus measure. But now we go beyond the linear case to the nonlinear PPDE. We need to consider more measures. So here, let tau and this x be the canonical process in the product space, the time and the space product space theta. And then we consider all those probability law such that the tau dimension will be a random variable taking value between 0 and capital T. And the path dimension will be a semi-martingale with coefficients mu and sigma bounded by L, almost surely. And this L is exactly the same L as the L Lipschitz of the generator G. Okay, that's why this simplifies the story. But in fact, for those non-Lipschitz G, we can modify the definition of the P round here and get a new definition. But it will be a little bit more complicated, so I will not talk about it in this talk. So let's consider the Lipschitz case, and that's the P round we will use. So instead, so recall that in the definition of for the heat equation, we use the optimal stopping maximum of tau and then expectation on the P naught. We will replace this operator by the nonlinear expectation, E round, defined as sup of the probability, the super over all the probability in the family P round. Let's take too long for this page. Okay, come back. So we will consider those nonlinear expectations defined as the sublinear and all superlinear expectation on for the path-dependent test function, for path-dependent functions. Okay. And now in the definition of jet, we simply, well, replace the linear stuff by the nonlinear stuff. And this is our definition of P-round jet. And then P-round jet, of course, lead to the definition of P-round viscosity solution for the nonlinear path-dependent PDE. So it's exactly the same formulation. You put alpha as the vertical derivative, beta as the alpha is the horizontal derivative, and beta is the vertical derivative, gamma is the second one. And then a viscosity solution is both sub and super solution. Now, natural question, is it a good definition? So again, it's a story really about comparison and so on. So this is the thing we will talk about in the next section. So what kind of properties we can expect from this definition, this P-round viscosity solution? So till now, I haven't mentioned what kind of distance I will use in the product space, because till now it's not important, but from here I will emphasize it. So we will introduce the distance dp defined on this product space theta, which is, well, P comes from the LP comes from the LP norm on the stop the path space. Okay, so the dp is composed of two parts: the difference of t and the difference of the stop the path. And this difference is described on the LP norm. So first, and very important, is the stability result. So the stability result is stated in such a way, which is almost the same as the classical literature for PDE in finite dimension. Okay, here the stability is the stability of the jets. So given a sequence of theta n convergent to the given point theta in the product space, and a sequence of un converging in some sense to the target function u, then okay, the stability result states that for any point, for any triple in the subjet of u at the point theta, if we give a little perturbation to this triple, it will still be in the subjet of a function nearby at a point nearby. Okay, so of un at the point theta n. So this is stability of the jet. It's exactly the same sense as in the classical literature for the viscosity solution of PDE in finite dimension. So, and as condition, we only assume that un are d infinity upper semi-continuous. Okay, this is also important because if you compare those dp distance, you will find that the d infinity continuity is the weakest among all those dp continuity. Okay. So we have this stability for quite irregular, if you want, functions. So this is a stability result. We will use it later. And then of course it's about a comparison. It's very important for the viscosity solution. So in the paper of Ikran, Tuzi, and Zhang, which is the first paper on this literature about the comparison for fully nonlinear path-dependent PDE, they prove such a result. They say that if the G, the generator of the PPDE, is uniformly d infinity continuous and uniformly elliptic, of course based on those assumptions I already made at the beginning of the talk, those three colors, if you remember. Okay, then we have the comparison for uniform d infinity continuous viscosity sub and super solutions. So how do they make it? So in this paper, the argument is based on the so-called frozen path PDE. In fact, the authors of the paper, they constructed the solution of the path-dependent PDE by pasting the solution of PDE piece by piece. Okay, since here the generator is assumed to be uniformly elliptic, the solution of the pasted PDE should be smooth. Then the solution of the PPDE will inherit this kind of regularity, and this kind of regularity will make the comparison to be proved easily. Okay, that's why the uniform ellipticity is very important in their argument. And in a more recent paper, we have proved the comparison without the constraint of a uniform elliptic generator. So I don't want to go deeper in the argument for this result, but I just want to compare these two. So as I said, in the second result, we removed the uniform elliptic condition on the generator G, but we make some sacrifice. So the sacrifice is that instead of assuming G is d infinity continuous, we emphasize, we ask something more. So we say that it must be dp continuous. And we only compare those sub and super solutions which are dp uniformly continuous. Okay, so we are comparing less sub and we are comparing fewer sub and super solutions. So in this sense, the result is a little bit weaker, but of course we removed the uniform elliptic condition. So in that sense, it's become better. Okay, so this is the trade-off. The trade-off is, well, dp continuity is stronger than dp infinity, d infinity continuity, but we get a comparison with less condition on the generator G. Okay, that's a comparison between those two results. And before moving on, there's some more things to tell you on this page. So for both results, there are something very bad hidden inside. That's the underlined part. So we ask the generator G to be uniformly dp continuous or d infinity continuous and uniform in all other arguments. Okay. So if we assume this kind of uniform continuity, we will exclude a lot of application of HGB equations. But this is a technical problem. We haven't solved it yet. So, but in the following talk, we can say something about it. So let's see. So here, the next section is about the connection of this kind of PPD. Sorry, it's PPD. It's not PDE. Okay. Sorry. That's right. Okay. It's connection of the PPD to the PDE on the Hilbert space. So what do I mean? So again, we come back to the suspicion left in the previous part of the talk. So I say there's some small issues to talk about for the horizontal derivative dt. So let's think about what's the definition of derivative. Okay, so intuitively, derivative is the generator of the translation group. And if we only think about the derivative on the right-hand side, it is the generator of a semigroup. And horizontal derivative is already mentioned, defined in such a fashion. And of course, we can find the corresponding semigroup H around, defined in such a way. And we note that, first, it's not a semigroup for OV on the product space. It's only a semigroup for those non-anticipative functions. Okay. So it's really a derivative only for non-anticipative functions. And it is not a semigroup only involving the t dimension, the time dimension. It also involves the omega thing, because okay, you make some change here. And which means the horizontal derivative indeed not a t derivative. That's why I never call it a t derivative. It is not. And what it is, can we replace it by some more classic derivatives? Of course, yes. Now we need to introduce the Hilbert space. So introduce the Hilbert space is the product space of the L2 space of paths, L2 space of paths from on the time horizon minus infinity to 0, and the real space of the RD. And now we want to embed the product space theta into this Hilbert space H and define the corresponding function capital V based on our function V, value function on the product space. Okay, how we do that? So we define capital V in such a way through embedding. So how to embed it? So given a path omega in our path space, so for the green part, the RD part of the Hilbert space, it's easy. We just record the final value of the stopped path. So we only record the value of omega t for the green part. And it's a bit more tricky for the orange part, L2. So what do we record here? So given a path omega in the continuous path space, we will define a backflash omega, which involves in the inverse way of omega. So, well, just think about this omega with this time horizon goes to infinity, positive infinity. And if you take it here as, so this is time t here. In the new coordinates, you set this point as time 0, and you follow the same path in the inverse way. That's the definition of omega backslash. Okay, and the omega backslash is an element in the L2 space, L2 path space. And that's how we embed the product theta in, we project the path space into the Hilbert space and define the corresponding capital V. Okay, the capital V is a function on time horizon times h. Okay, here is a typo. It's not on h. All right. Of course, under some uniform continuity condition, for example, we can extend the definition of V to the whole space of H. Okay, here is only defined on part of the H if you only consider those omega which are continuous, but then you can extend it. So, again, we come back to the definition of horizontal derivative. So for the horizontal derivative, we do such a perturbation for the v function, for the little v function, and correspondingly, we have such a perturbation for the capital V function. And we just give a name to this perturbation using an operator SH, okay? And in fact, we can simply prove this SH is a semigroup. SH is a semigroup. From this semigroup on this Hilbert space. Therefore, the horizontal derivative has this calculus. By admitting the simple chain rule, you see that the horizontal derivative in dubious sense is composed of two parts. First, it's the d bar t, which is the classic t derivative of the capital V function, plus the other part, which is the gradient, well, in the Godot sense of the function capital V functioning on AX, and A is the generator of the semigroup S. Okay, and for this semigroup, in particular, the A operator is unbounded. Okay, well, as usual for semigroup in the general case. Okay, so we find this A unbounded generator. And now, of course, we can replace the horizontal derivative by the composition here and find a twin equation for our PPD, which is defined on the Hilbert space. So, well, this is just about notation, and we just talked about horizontal derivative, but in fact, for the vertical derivative, it's evident. We can, by the definition of the embedding, we can identify that the vertical derivative is, in fact, the same thing as the derivative on the green part. Okay, on the green part of the Hilbert space. So, by identifying both horizontal derivative and the vertical derivative, we can write down the twin equation on the Hilbert space, which is stated as the following way, okay? So you just replace the dt small u by this term, the term we just talked about. So equation 1 is PPDE, equation 2 is PDE on Hilbert space. And of course, there's a big amount of literature on the second equation already. Well, it's initiated by Pierre-Louis in 1990s. And the classical way to treat it, the classical way to define viscosity and to prove the corresponding comparison principle is to introduce an auxiliary operator B. Okay, so B is a strictly positive and self-joint operator on the Hilbert space, and well, it has a constraint. This is so-called weak condition, weak B condition. Well, we don't need to read the detail here. That's why I put it in green. So the point is, the definition of B depends on A. Okay. And in the literature, we talk about this B. Okay. And the definition of the viscosity solution will depend on this B operator. And because of technical constraint, we can only talk about the properties of B continuous B viscosity solutions in the literature. And what is B continuity? Well, since B is a strictly positive and self-joint operator, we can introduce a B norm from this norm on the Hilbert space. And in fact, B continuity. And if the B operator is compact, then B continuity is a sort of regularity between the L2 continuity and the B norm continuity. Okay. Yes, well, this is not so important for this talk. Just to remind you that. And now, so in this page we see the twin equation, but we haven't connected our definition of P-round solution to the classical definition of this B viscosity solution. So this is the content of the next page. So if we define a new distance on the product space theta, or using this B norm, okay, now we use B norm, we replace the LP norm by this B norm, we define the new dB. And then if a viscosity solution or subsolution is dB continuous, a P-round viscosity solution is dB continuous, then we can prove that the corresponding capital U is a B viscosity solutions of the PDE on the Hilbert space. Okay, therefore, we can, of course, borrow the result in the literature of Hilbert space PDE to prove the comparison. For example, we can use the result by Switch in 1994. So in his paper, we no longer need the uniform continuity condition on this generator G. Well, this is the advantage in particular. Okay, so as I said, in our effort before, we can never remove the uniform continuity of the generator G, but if we consider dB continuous viscosity, P-round viscosity solution, then we can remove that technique constraint by using the result of PDEs on Hilbert space. But we need the dB continuity. Notice that the dB continuity is, in fact worse than the dB continuities. And there are a lot of applications in which the value function cannot be dB continuous. So it's again a trade-off between the regularity of the solution we want to compare and the requirement of the generator G. So we do another trade-off, okay? But I'm not saying the trade-off is necessary. We are just not able to prove it now, okay? But well, if we want to use this result, we'll make this trade-off. Okay, now, finally, we will talk about the application of the PPT. So why we consider the nonlinear control problem? Is that so interesting? So just think about the reality. The computer can hardly solve the even we can write down the PPT, okay, on the path space. But since it's on the path space, infinite dimensional path space, it's very hard to get efficient numerical solution for such a PVDE. So even we have already proved the convergence of such schemes, but well, it's totally not acceptable in performance. Okay, so so before we have the next generation of computer, what do we expect from this PVDE theorem? What do we want? So in fact, well, through this example, what I want to present is that there are some analytic interest in studying it. So here, I give an example about a control problem with delays. If you remember at the beginning of the motivation, we have already mentioned a control problem with delay, okay, of information. So a more concrete example would be, if one day you want to buy a house, you want a mortgage, right? Normally people don't buy houses in cash, you want a mortgage. So you go to the bank, and in order to get your loan, the bank will ask for a certificate of your salary income during the past 3 months at least. Okay, so this 3 months is exactly the delay we talk about today. So there's a delay of information. There's a window of delay. So the salary you get in these 3 months will determine whether you can get or not the loan you need. Okay, that will determine your optimal utility problem. Okay. So in this generator, in such a problem, in such a control problem, your consumption, your utility will be T minus delta, will be delta delayed. So if you write down the Hamilton-Jacobi-Bellman equation, it will have such a form, okay, with the dependence of omega T minus delta. And since we have already quite a general stability result, we can expect that when delta goes to 0, the solution will converge to the solution of the PDE. Okay, the PPD will degenerate to a PD. And of course, PD can be solved. We are very happy about that. And what's more, we can talk about it. So how about the convergence rate in such a form? The U delta minus U over delta. So we want to study this asymptotic behavior of this approximation. This is the first order expansion of this approximation, right? And we want to calculate it explicitly using our PPDE result. So how it helps us? So let's see. First, I define an accelerated process H delta, I call. So that's why I put it in gray. You don't need to read it in detail. Just remember that H delta is a value of conditional expectation, so it will fit some linear equation, some sort of heat equation, linear equation. And the semi-martingale we plug in is driven by this dynamics. Okay, so well, that's all. Just remember there's a auxiliary process H. And in fact, what we can prove in the next page is that the limit of this asymptotic is in fact the same as the limit of H delta. And the limit of H delta can be calculated by hand. Okay, can be calculated by hand. So in such a way, we can compute the limit of the first order expansion. Okay, we can calculate the error of first order. Okay, how we do it? So how to prove this blue line here? So we just consider the difference between this quotient and H delta, right? We want to prove that V delta converge to V equal to 0. We want to prove that this V will finally prove that this V is 0, okay? We want to prove V is 0. How we do that? Of course, we want to write down the equation for V delta. So it's just the intuitive calculus. Everyone can follow. So by definition of V delta, you just write down the horizontal derivative of V delta in such a way. Well, just do it for the right-hand side. And then since U delta and U satisfy their own HGB equation, one is past dependent, one is not. So you have the second line. And the third line, just a simple trick to add and minus the same term in green. Okay, same term in green. And then you do the Taylor expansion. You do the Taylor expansion intuitively. So for the first one, the Taylor expansion will give you this term as first order. And for the second one, it will give you this it will give you the green thing. Yes. No. For the second one, it will give you the second line. Okay. First line, second line. Okay, and then I noticed the term in blue. The term in blue is in fact the equation that H delta will satisfy. As I said, H delta is defined as the conditional expectation, so it must be a solution of a linear equation. Here, the blue terms are exactly the linear equation H delta will satisfy, so it will be equal to 0. So if we omit the high order term, you find the equation in red. Okay, so finally you get dTv delta is equal to minus g gamma, blah, blah, blah. So this is a linear equation, path-dependent equation. And of course, you have a high order term, O1, and then you just let delta go to 0 using our stability result again. You prove. Of course, here you need a comparison result too, anyway, in technique. So using this, our stability result, mainly, you can prove that the limit V satisfy indeed the linear equation, this linear equation. And taking into account at the terminal time, V, by definition, V capital T is 0, of course, the unique solution satisfying this linear equation will be 0 everywhere. So finally, we prove that this limit is 0, and we solve the first order. We calculated the first order error for these asymptotics. So this is application of our PPD result. Here you see, okay, there is the useful passage of stability argument and comparison both. So okay, so let's conclude. About this talk. So first, at the first glance, PPD is motivated by this nonlinear Markov control or differential game. So we want to go beyond the PD case, the PD in finite dimension case. That's why I proposed the PPD. And then technically, because of the notion of path derivative introduced by Bruno Dubir, it makes a functional etocal calculus possible, and the functional etocal calculus justify the form of PPD. And in our definition of P-round viscosity solution, we replace the classical definition with the local maximum by the local maximum in the sense of mean value. That's why it depends on P-round. And we have a quite general stability result, which only requires the sub-solution or super-solution to be d infinity semi-continuous. And we have a lot discussion about the comparison, and we find it's usually a trade-off between the regularity of the compared solution and the condition we want to make on the generator G. Okay, but again, I don't mean the trade-off is necessary. It's just a technical issue. If one day you guys can prove it in a more pretty way, that will be better. So then we mentioned the connection between the PPD and the PD in the Hilbert space by the simple embedding. And again, the literature about the PD in the Hilbert space needs the regularity of B continuous. Regularity of B continuity. That's a technical restraint. And for PPD, at least formally, you don't need it. You can talk about the solution in the sense of dP continuity. Yeah, and then we talk about application, mainly using the stability argument. We say that in fact those models in finance, in physics, so we can consider they are still stable even if the model is become path dependent. Okay, It's stability in a more general sense. And furthermore, we can use our knowledge on the PVDE to calculate some asymptotic behavior of this kind of path-dependent perturbation. Okay, we only consider the delay perturbation, but of course, maybe you can consider something interesting you more. Well, that's all for this talk. Thank you for your attention.
Thank you very much.